What I tell you 3 times is true. Is that statement by Lewis Carroll true? Well, I hope you know, given that this is Chem Activity 1 in the Chem 112 course, and that we will be talking about accuracy, precision, and significant figures, that this statement indeed is not true. I can tell you a lie 3 times. And of course, telling you 3 times does not make that lie a true statement. Lewis Carroll, of course, is the author of Alice in Wonderland, a famous children's book, but this quote does not come from Alice in Wonderland, but rather from the poem called Hunting of the Snark. In this set of videos, we will explore the concepts of error, accuracy and precision, significant figures, and calculations involving significant figures. The intended learning outcomes are that you will be able to distinguish between accuracy and precision and assess the limitations of various measuring devices, for example, the pipette versus the graduated cylinder. Also that you will be able to record measurements and perform algebraic calculations using the correct number of significant figures. I would like you to imagine that we have collected a number of pieces of data, and this data is represented by the little dots that are on the scale. I have indicated where the true value is. I've also indicated that because each of those dots is a piece of data, we can find the average or the mean. Considering this diagram and then considering the definitions that are given under Teaching Model 1 for accuracy and precision, I would like you to think about where in the diagram the concept of precision is represented, and where in the diagram the concept of accuracy is represented. Given that accuracy is how close a measurement is to a true value, the line right here from the mean to the indicated true value gives us a sense of how accurate these data are collectively. Of course, you can also reflect on the accuracy of each individual point, but it is more common to focus on the mean of the data. If we consider a range of data points, we then get a sense of precision. The precision is the degree of reproducibility of a series of measurements made using the same procedure. If you have a high variation, then you have a low precision. In this example, we can see that the experiment was repeated several times, yet different values were measured. An assessment of accuracy and precision, however, is not an absolute determination. Rather, it is usually more helpful to compare sets of data for their relative accuracy and precision. I would like to develop this further. Let us take a look at some data that we might collect in the lab. For instance, in Teaching Model Number 2, we see data that were collected by students to determine the boiling temperature of water. There were 3 groups of students, and each group collected 3 pieces of data. That is, they performed the experiment in triplicate. These are repeated measurements using the same procedure. Therefore, we can appropriately reflect on the precision. We will also assume that the accepted value for the boiling point of water is 100 degrees Celsius. Because we have a true value, we can reflect on the accuracy of each data set. Look at the key questions 1 to 3 to explore this data. In terms of an explanation, you may consider jotting down some notes. As you determine, Group 3's data was collectively the most accurate, that is, closest to the true value. Group 1's data, although not very accurate, shows the smallest variability, all within 1 degree Celsius, and therefore is the most precise. Given that Group 1's data points are all below the true value, there must be some kind of systematic error at play in their data collection. We will see in the lab that we can use a calculation of percent difference to reflect the relative accuracy and standard deviation to reflect the relative precision. It is worth mentioning that sometimes it's quite difficult to determine the accuracy of data because often we do not have an accepted true value. And when we do have a true value, many times this value is simply an arbitrary value, agreed upon by the scientific community. In teaching Model 3, we see some data concerning time, taken with different timekeeping devices. We have an analog watch, we have a digital watch, and of course we have Doug's sundial, which can be considered as a rather large watch. We also have, in a sense, the true value for time, which comes from the Bureau of Standards time. Please consider the key questions 4 through to 6. Jerry's analog watch is the most accurate, as its measurement of time is closest to the true value. But which watch is the most precise? You may be wondering how it is that we can evaluate precision when there's only one measurement. Jen's digital watch is the most precise. This is because her measurement has the most significant figures. Significant figures are all the certain digits plus one more, which is estimated at by making a discerning guess. We need to clarify a little bit, however, what we mean by certain. In this case, certain does not mean accurate, nor does it mean true. Rather, certain means that if we repeat a measurement, we will arrive at the exact same value again. In terms of Jen's digital watch, and assuming the time has not changed, we are certain that we will measure the 9, the 1, the 7, the 5, and we're guessing at the 2. Whereas with Jerry's analog watch, we are only certain about the 9, the 1, but we're guessing at the 5. We can think, therefore, of significant figures as being a short form to represent or indicate a probable precision. The chances of obtaining the exact same measurement for the certain digits would be very high, but very low for those digits for which we are making a guess. Again, certainty does not reflect the accuracy. A small caveat to this, however. An instrument that has greater precision has the potential for greater accuracy. To help you understand what I mean, let us say that Jen's digital watch actually measured a value of 9, 15, 12. Jen's digital watch would be the most precise, of course, and compared to Jerry's analog watch, Jen's watch would also be the most accurate. In this case, having greater precision, the measured value creeps closer to the true value. Back to significant figures. Because significant figures tells us about probable precision, when we are making experimental measurements, it is important to record the values to the correct number of significant figures. Teaching Model 4 gives us some practice in this. Here is somewhat of an interactive animation. The idea is that I want to measure the diameter of the circle using two different rulers. Using the top ruler, we want to measure to the correct number of significant figures the diameter of this circle. We would be correct in writing the number 2 for the first digit, as we are certain that the diameter is at least 2 centimeters. Then we might think the next digit is a 3. We might even try to add an extra digit, let us say 0. If we submit, our answer is marked incorrect. We are told that we cannot measure 3 significant figures with this ruler. We try again. And indeed, given the graduations on the ruler, where we are certain about the 2, and we're actually guessing about the next digit, therefore we can report the measurement as only 2.3. We then submit. The correct measurement contains 2 significant figures. We are certain about the 2, and we are guessing about the 3. To make this point further, If we now insert 2.2 and submit, we're also told that this is the correct answer. Let us now use a more precise ruler. If we move the circle down and try to line it up appropriately, we are certain about the 2 and the second 2 in the first decimal place, but we're guessing about the second decimal place. We think the number might be 2.27, so we try this number. When we click Submit, we're told that the number is correct. Let us also try 2.28. This is also considered correct. Again, we are guessing at the second decimal place. The following is a video of a liquid draining from a 100 ml graduated cylinder. The video will pause at a particular volume. Please record the volume to the correct number of significant figures using the principles we discussed in the ruler measurement. Remember to read at the bottom of the meniscus. The next video shows a liquid draining from a 50 ml burette. This video will pause at a particular marking on the burette. Please record the indicated value to the correct number of significant figures using the principles we discussed with the ruler measurement. Again, remember to read to the bottom of the meniscus, and keep in mind that the 0 mark is at the top of the glassware.